What I'm going to look at in this video is I'm going to look at matrix multiplication. Now when I'm referring to that in this video, I'm talking about the process of multiplying two matrices together, rather than taking a single matrix and multiplying the whole thing by a scalar. Now there's a couple of characteristics and properties that must be associated with both matrices in order to be able to do this, and there's a set technique. Now when I explain the technique to you at first, you might think to yourself, oh, that's a wee bit trickier than I'd thought, but actually once it's put into practice and you start repeating the technique over and over, it actually becomes quite clear, quite straightforward, and we're able to manage it from there. So we just have to bear it in mind, it's not quite as complex as it looks. It does get easier as we practice. Now, in order to look at the multiplication of two matrices together, what I'm first going to do is I'm going to define the product of a row and column as the scalar product of two vectors that can be represented by the row and the column. So let's imagine I've got the row of one matrix given by 1, 2, 3, and I've got the column of another matrix given by 3, -1, 0. What I'm going to do is I'm going to define the scalar product as taking both of these and representing them, if you like, as a vector, and then following the same process we would for scalar product of two vectors. So I'm going to multiply the first terms together, second terms, third terms, and then I'm going to find the sum of all three of them. So I'd have 3 times 1, my first terms together, then plus -1 times 2, the second terms together, then plus 0 times 3, my third terms together. And then it's just simplifying it. So calculating each of these and adding them up. So I'd have 3 take away 2 plus 0, so I'd get 1. So when I'm talking about the scalar product of two vectors for a set row and a column, this is the process I'm talking about. It's the exact same as the scalar product of two vectors. All we're doing is letting the vectors in this case represent the row and the column we're referring to. Now what I'm going to do is I'm going to take a matrix C and I'm going to define it as AB, i.e. the product of two matrices A and B. And what I'm going to tell you is that matrix A has order Mn and matrix B has order Np respectively in my definition. What that means is I can then use this and this scalar product to define any element of C within this new matrix I'm going to make. Now before I tell you that, there's one key thing you need to notice, and that is the number of columns in A has to match the number of rows in B in order for this to be able to work. Those two properties of the matrices have to be the same. If they are not equivalent, we cannot multiply the two matrices together. And you'll see why in just a second. But that is a characteristic we should always bear in mind. If they do not work, if they are not the same, we cannot multiply the two matrices together because it will not work. Now any element of C can be defined in this manner here. So Cij, a generic element somewhere in the matrix C, what I'm going to do is I'm going to take the ith row of A and I'm going to do the scalar product with the jth column of B. So essentially I'm going to do the same thing I've done up here, where one vector essentially is going to be represented by the ith row of A, the second vector is going to be represented by the jth column of B. So that would mean, if I looked at it in individual terms, my ith row would be AI1, AI2, AI3, so on, up to AIN. Now I know I can define an n there because the column and the row of any matrix has to end at some point. So I'm only going to have at most n terms. I've then got my jth column of B, so B1j, B2j, B3j, etc., all the way down to Bnj. Again, there's only a set number of terms in that column, so I can define my final term. And you'll notice that the n is the last element in the row and the column. What I then do is treat it as I did the scalar product, so multiply together corresponding terms, i.e. the first term in each, second term in each, third term in each, and so on, and then calculate the sum of all these values. And that's what this line here represents. So first row and column element, second row and column element, third row and column element, etc., all the way up to the final one. So that means any element in my matrix C is the ijth element of it can be represented by calculating this. So the sum from k goes 1 to n of aik times bkj. So the sum of the multiples of a row of one matrix times the column of another. Now it looks a lot more complex than it is, but actually, trust me, when we do a couple of examples for you in a minute, you'll see exactly what I mean and how easy and straightforward it actually is. Now a couple of things just to highlight to you. First things first, the big thing I just mentioned there, this definition will only work when the number of columns in A is the equivalent of the number of rows in B. It's a necessary condition for this to work and for the two matrices to be compatible for multiplication. And another key thing to remember for this is that A and B may be compatible to form the product AB, but they may not be compatible to form the product BA. So we have to make sure we get our matrices the correct way round for multiplication. Now the product of an m by n matrix and an n by p matrix, this gives a matrix, obviously as our final solution, but this matrix will be of order MP. So this will be a matrix of order m by p, rows and columns. So for example, product of a 2 by 3 matrix and a 3 by 1 matrix will give us a 2 by 1 matrix as our solution. Think of it in terms of dominoes. If I've got two sets of dominoes, this is my first domino, so let that represent the dimensions for A. This is my second domino, so let that represent dimensions for B. So if you like, my number of columns for A and my number of rows for B match up. If I was to eliminate the two of those, I'd be left with my 2 and my 1, so my final matrix, which we call our C, would have dimensions of 2 by 1. Okay? These are a couple of the key things that have to be in play and you have to notice in order for matrix multiplication to occur. Now again, throwing lots at you here, it may be looking at it going, what is he going on about? This looks really complex. But actually, set technique to follow makes it straightforward. I'm going to give you an example of that, which will hopefully put you at ease. So let's evaluate two matrices. So I'm going to evaluate the product of this matrix here, let's call it A, and this matrix here, let's call it B. Now matrix A is a 2 by 2 matrix, and matrix B is a 2 by 3 matrix. Now what this means is the number of columns in A, which is 2, matches the number of rows in B, which is also 2, so I can say safely that A and B are compatible for multiplication. So I can multiply the two of those together in order to get a solution. And I can then also look at it and say, well, if that's the case, then my solution should end up giving me a 2 by 3 matrix. So it'll be similar to this one here. But obviously the elements within it will be different. So what do I now do to get all my entries? Well, to do AB, there's a quick and easy way to remember it. This element here, what we do is if you take the first row of this one and multiply it by the first row, the first column, here, that will give you the element in your second matrix, your solution, which is in the first row and the first column. So my first entry into this matrix AB would be given by 8 times 2 plus 6 times 7. I could then continue this on for every single column. So I'd then say fine, so this row here and this column is my first row and my second column. So that would then give me the entry in this one that corresponds to that. So my first row, my second column entry, that would then be 8 times 4 plus 6 times 1. I could then do it a final time for my final column there, and I know for this one it's going to be the first row, third column of my solution. So it's going to be 8 times 5 plus 6 times the negative 2. I then move on to my second row for A. Alright, I've combined the first row with every column so far in B. I then move on to my second row of A. Once you run out of rows in A, you're finished. Once we run out of rows in A, we can't do any more multiplication between the two matrices, so we're done at that point. So again, this one, I would then take that row and do the exact same thing with each column. So the first one would be second row, first column, so it's going to give me the entry that corresponds to the second row and first column of my solution. So that would then give me -1 times 2 plus 3 times 7. Then do the row in the second column. That would then give me -1 times 4 plus 3 times 1. And then the second row in the third column would give me -1 times 5 plus 3 times the -2. So what I can now safely say is that because I have run out of rows in A, I can no longer do any more any more matrix multiplication within it. So now I just have to simplify each of these and I get the elements of my new matrix, so my solution. So if I were to do that, I'd have 8 times 2, which is 16, plus 6 sevens, which is 42. So I'd have 16 plus 42, so that would then give me 58 for that element. I'd then have 8 times 4, so 32 plus 6. So I'd have 38 for my second element there. And then this last one, I'd have 5 8s, which is 40. Then plus 6 times -2, so I'd have 40, take away 12. So I'd have 28 there. I then look at the second row. I've then got -1 times 2, so I've got -2 plus 21. So I'd get 19 for that element there. I've then got -1 times 4, so I've got -4 plus 3. So I'd have -1 there. And then this final one, I'd have -5, take away 6. So I'd have -11 there. And that there is a solution when we take the product of these two matrices A and B together. It's quite a straightforward set of steps, and actually using the lines in this step here helps. Yeah, just remember when we're taking the row and multiplying it by whatever column we've got, it corresponds to that row and column within my solution. So first row, first column gives me that solution in there. So first row, first column, so 1 1. First row, second column gives me that corresponding solution in my solution 1. So that will be entry 1 2. And we follow it through for every other entry within the matrix. And lo and behold as well, as we predicted at the start, our solution is a 2 by 3 matrix. So our solution is exactly the kind of solution that we were expecting to get at the end of it all. When we're multiplying two matrices together, remember these steps. If you can remember them, execute them and follow them through, it is a lot more straightforward than we'd hope, and a lot more straightforward than you'd expect, given all the jargon and all the information I've thrown at you just before this. It's not that difficult, just remember the technique.